welcome to our next part. So part 5 of chapter 1 is we're going to start talking about units of measure. And this is where we're going to talk about the numbers and work with the numbers that we're going to need to use to keep track of either these really, really big quantities or really small quantities of stuff that we look at in this conversion between the macro and the microscopic world. So underneath this topic of units of measure, we have our what we call SI units. That's our labels and our scales that we use. We'll talk about how these units of measure apply to both temperature, density, and then how we do something called unit conversions, the math that we actually utilize in order to convert from one set of units to another. And all of these things that we're going to talk about here are going to be really vital components in everything else that we talk about this semester and beyond. So if you have any questions at all, you need extra practice of this, let me know. You get stuck with any of this stuff, let me know right away, because this really needs to be second nature, really easy, really comfortable for you. And if you have any questions, let me help, and let's get you some resources so you do get really comfortable with this, because it will make your life a whole lot easier, much less stressful, this course and in other courses beyond. Okay. So let's look at our units of measure, our SI units, the International System of Units. This is things like for length we use meter, for mass we use kilogram, time is in seconds, temperature is in kelvins, amount of substances is a mole, we'll talk about that. And then those are our basic units, where it's just one symbol, one label applied to each thing. Length is always in terms of meters. We can derive some units by combining them together, things like volume, length times width times height. And that gives us a unit of an SI unit of meters cubed or cubic meter. Density is mass per volume, kilogram per cubic meter. And we can utilize some derived units. And there's a whole bunch of others that we're going to encounter as we move through this course and others, but they're all handled the exact same way. So this will be our baseline, our framework for how we handle and work with our International System of Units. So the next thing we need to do is look at prefixes, so we don't have to write out these big long numbers. Another way we can handle them, and why these SI units are so useful, is we can use these prefixes to represent really big or really small numbers. If you see the mega abbreviation, the capital M abbreviation applied to something like mass, kilograms, mkg would be mega kilograms, and that would represent 1 mkg would represent 1 million kilograms. 10 to the 6 kilograms. Same thing, kilo. We see this very often. A kilogram is 1,000 grams. Centimeters is 1/100th or 0.01 of a meter. And we can work our way all the way through. This is something I'm going to ask you to memorize, these list of prefixes. We're going to encounter them quite a bit, so especially something like kilo, centi, mega, micro, pico, and nano. Those are things that we're going to encounter quite often. So knowing what those abbreviations mean and these factors that are applied, whether it's the factor itself or the scientific notation, 10 to the negative or 10 to the whatever, those are going to be really important things to have memorized. So we have what we call conversion factors, how we can help switch between one set of units and another. And that's just a matter of applying these prefixes to our base unit. So in terms of length, our base unit is meters. So 1 centimeter is 10 to the negative 2 meters. 1 millimeter is 10 to the negative 3 meters. 1 nanometer is 10 to the negative 9 meters. And we can go from there. 1 angstrom is 10 to the negative 10 meters. And once you get into angstrom and picometers, that's on the atomic scale. The distances between the things that make up an atom, the neutron, electron, proton within an atom. The distances there are in the angstroms and picometers. We can actually measure down that small. We have this metric system that's what we're pretty much going to use ubiquitously throughout all of sciences. And then we have the English system. And what's complicated is here in the United States and a few other places in the world, a lot of what we work with in our daily lives is based on the English system. Inches, miles, things, pounds, things like that. Where the rest of the world, and in science specifically, is in the metric system with kilograms and meters and such. And we can convert back and forth, and here's some conversions here going back and forth. We're not going to do a lot of that because most everything that we measure and the numbers that we generate are already going to be in the metric system. So we're not going to have to convert between the English and the metric system all that often. Temperature is one of those things that we're going to encounter all the time, and that can be measured in one of 3 different ways, whether we talk about the Kelvin scale, the Celsius scale, or the Fahrenheit scale. Fahrenheit scale is the English scale. That's the one that is going to be used the least. That's the least common in the scientific world. Celsius and Kelvin are pretty much used interchangeably. Typically, we measure in the Celsius scale. We would do our math in terms of the Kelvin scale. So there's a very common conversion, and it's a very simple conversion between Celsius and Kelvin. And what you can see is if you look at the thermometers here, they're all doing the same thing. They're all in an ice water bath. And what we're looking at is where the freezing point and boiling point of water is with respect to these three scales. So if I look at the Fahrenheit scale, I see that water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. For Celsius, we set this at Celsius. We set the freezing point for water to be 0 degrees Celsius and the boiling point to be 100 degrees. So we created that to fit within that range. We said, okay, water is such an important compound. We're going to use that as our base for our Celsius scale. And the freezing point of water we're going to say is 0. The Celsius scale, the boiling point is going to be 100 degrees, and then we'll fit everything else in between that. And then the Kelvin scale was developed afterwards is an absolute scale. So here, water freezes at 273 degrees Kelvin and boils at 373 degrees Kelvin. So if you look carefully at the Celsius and Kelvin, you'll see a very easy conversion between when water freezes or when water boils. So on the absolute scale, the Kelvin scale, we needed that because for our calculations that we need to do, it's impossible to have negative temperatures, right? So if we use either the Fahrenheit or Celsius scale, we can clearly see that negative temperatures are possible. And the math that we need to do, some of our calculations, won't allow us to have a negative temperature value. So we needed this absolute temperature scale to always provide us with a positive value. So in terms of Kelvin, the lowest possible temperature is 0. You cannot have a negative Kelvin value. That is absolutely possible. We can't actually reach 0 degrees Kelvin. That even in the deepest of space, the coldest place that's ever existed doesn't actually get to 0 degrees Kelvin. There's always a little energy present. It might be very, very small. It might be really close to 0 degrees Kelvin, but it's not actually there. So we can do some conversions between Celsius and Kelvin. So that's really simple. Kelvin is simply Celsius plus 273.15, or usually just 273 is good enough to convert between Celsius and Kelvin. Therefore, to convert from Kelvin to Celsius, it's just Kelvin minus 273. For Fahrenheit, it's a little bit more complicated. The equation is here, going back from Celsius to Fahrenheit or Fahrenheit to Celsius. And this will be something that you'll encounter occasionally, and it'll be on our equation sheets. Okay. So when I convert between units, it's called either unit analysis, or what the term I like to use is dimensional analysis. But both of these phrases describe the same thing, switching from one set of units to another. And there's a really simple process that we can go through and follow that. So let's explore that process using this example, a common example of just going from hours to minutes. In this case, we'll go from 48 hours to minutes. So the first step is write the quantity in the current units and identify the new unit. So basically, we write it our 48 hours plus our conversion of whatever we need to do to switch into minutes. So what this does, this tells us units that we're starting with and the units that we're ending with. So we can figure out how do we make that conversion from one thing to the other. And that's what that conversion factor is. So we're going to relate the current units of hours to the desired units in minutes as a ratio. So we're going to write a ratio that's going to switch between those units. So we know that 1 hour is equal to 60 minutes, so we can write that as a ratio. 1 hour per 60 minutes, or I could write it as 60 minutes per 1 hour. And how we set that ratio up is just going to be dependent on what we're going from, what set of units we're going from, to what set of units we're going to. So this ratio and the arrangement of this ratio is completely up to us, and we create it as necessary to allow us to do the conversion that we need to do. So this conversion factor is this ratio of two different units used as a multiplier to change from one system to another. And that's what we have here in terms of going from hours to minutes. So of these two conversion factors, 1 hour per 60 minutes or 60 minutes per 1 hour, which one do you think we need to use? And the answer is 60 minutes per 1 hour. And I'll show you why as we go through this. So continuing with the same example, our step 3 is we're going to multiply the original value by the conversion factor so that the original units are canceled by the same units in the denominator. So what that means is I want the denominator of my conversion to have the same units as my original value. So I started with hours, so my denominator has to have hours. And because of that, the hours cancel off and the hour units are no longer there. So now I can lastly perform the multiplication of just the 48 times the 60, and I get an answer of 2,880 minutes. Okay. This third step, going back here, where I write out the units, is really important. That's the step that everybody always skips because it's just faster to do 48 times 60 divided by 1, and you just in your head know that the hours are going to cancel off. And with practice, that may be true. But when people do these conversions, inherently when they make mistakes, it's because they haven't set up the ratios properly, because they didn't cancel off the units. So always, always, always write your units when you do these conversions. It will guarantee that you cross off and you have it set up properly. And then go through the process of actually crossing off the units to make sure that they do cancel away. And the only units that you have left when you finish that process on the left side of the equal sign will be the same units that you have on the right side. Once you have that, then you know you've set the conversion up properly, and now it's just a simple matter of doing the math of pushing the numbers in your calculator. And come exam time, setting this up properly makes the process actually faster, especially when you go back to check your work. If you know your units all cancel off, then if you want to check your work, all you have to do is check the math, and that's just retyping the numbers in the calculator. You don't have to reset the problem up and think your way through it all again. You know you've done it properly. So again, when I do the math here, I want to make sure those units cancel off, the hours cancel, I'm left with minutes, and I can figure out my answer. So take a minute and go through this and figure out which of these lengths is represents the longest value, which of these is the greatest length. Right. So to do this, we need to convert these all to the same set of units. And I can pick whichever of these units I want to convert everything else to. But meters are our base unit. That's going to be the easiest thing to convert into. So that's what I'm going to do. I'm going to convert all of these into units of meters. So going back using that conversion that we talked about a few slides ago, let's convert option A, 5.80 times 10 to the 8th picometers. So I know 1 picometer is 10 to the minus 12 meters. And because I'm looking to get rid of picometers, I put that in my denominator. So picometers cancel. I'm left with just meters, so I do that multiplication, and I get 5 times 10 to the minus 4 meters. We'll do the same process for B. Now I'm not in picometers, but I'm in nanometers, so I look up that conversion. I want my meters in the numerator, nanometers in the denominator. That allows me to multiply and cross off the nanometers. Those cancel off. Doing my multiplication, I get 5 times 10 to the minus 3 meters. Looking at C, now I'm in terms of micrometers. Find my conversion there, 1 times 10 to the minus 6 meters per micrometer. I'll multiply by the conversion factor. The micrometers cancel, and I'm left with 5 times 10 to the minus 6 meters. Finally, we'll do it in terms of millimeters. My conversion there is 1 times 10 to the minus 3 meters per millimeter. Multiplied by a conversion factor, millimeters cancel. I get 5 times 10 to the minus 4 meters. And option E, I don't have to change at all because that is already in terms of meters. So what I see here is that options A and D are actually the same length. When I put that in the same scale, they're both 5 times 10 to the minus 4 meters. And option B is going to be the greatest. That has the smallest negative exponent. So that represents the largest value. So B is the greatest length here. All right, so let's try this question. So the radius of a circle is 2 micrometers. What is the radius in terms of millimeters? So take a minute and go ahead and answer this one. All right, so here we want to go through and convert from micrometers first to meters. So we're going to do that. We're going to go from 2 micrometers, and we're going to convert that into our base unit of meters. So that's going to allow us to cancel off the micrometers. And then we're going to go from meters to millimeters. So now our meters cancel away, and I'm left with units of millimeters. That checks off. That's the units I need to end up with. Now it's just a matter of doing the multiplication. So here we have an example of doing 2 conversions. And this is the easiest way to go through this. Even though this is a 2-step process, it's a lot less cumbersome and a lot less confusing to do it this way than to try to go directly from micrometers to millimeters. So the answer here now is 2 times 10 to the minus 10 millimeters. So B is going to be your correct answer here. All right. Now, let's look at volume, our first of our derived units. So we have a couple conversions here for volume. 1 cubic centimeter is the same thing as 1 milliliter, and 1 liter is the same thing as 1,000 milliliters. So those are some very, very common conversions that we use all the time with volume. So that might be something you want to add to your memorization list. So here's a question. A beaker has a volume of 250 milliliters. And now let's convert its volume into cubic centimeters, into liters, and into cubic meters. So A is very simple, very straightforward. 250 milliliters. Our conversion there is 1 cubic centimeter per milliliter, so it doesn't actually change anything. So I can cross off my milliliters and I'm left with 250 cubic centimeters. Very often, because it's a one-to-one conversion, we don't even really do this step and we'll just cross the units off and change to the appropriate unit, whether it's milliliters to cubic centimeters or vice versa. Now let's look at option B, converting to liters. I have 250 milliliters. My conversion there is 1 liter per 1,000 milliliters. The milliliters will cancel. And I'm left with 0.25 liters. And again, with practice, this conversion is also often done in our head as well. It's just by shifting things the decimal point 3 places, changing it by a factor of 1,000, either to the left or to the right, depending on whether we're going from milliliters to liters or liters to milliliters. Option C is a little bit more challenging. So let's flip to a clean screen and convert this into cubic meters. So we know 1 meter is the same thing as 10 times 2 centimeters, 10 squared centimeters. So that means 1 square meter, but in area, is 10 to the 2 centimeters squared, or 10 to the 4 square centimeters. So that goes me from length to area. Now to go from area to volume, I need to cube it. So cubic meter is 1 times 10 to the 3 meters. And then a cubic centimeter would be 1 times 10 squared centimeters cubed, or 10 to the 6th cubic centimeters. So now that I've built my conversion factor, I can go through. Now I've got a value for cubic centimeters and cubic meters. So I have 250 milliliters. We'll convert that to cubic centimeters, a one-to-one conversion there. So the milliliters will cancel. And now we've constructed our conversion from cubic centimeters to cubic meters. 1 cubic meter is 10 to the 6th cubic centimeters. And now our cubic centimeters disappear. I'm left with cubic meters, where I want to end up. And I do that math. I get 250 times 10 to the minus 6 cubic meters. The correct way in terms of scientific notation would be 2.5 times 10 to the minus 4 cubic meters. Those would be the exact same answer. Let's look at density. So density allows the conversion between mass and volume of a substance. So density is mass divided by volume. Usually this is referred to in terms of grams per milliliter for liquids and solids, or grams per liter for gases. Occasionally you'll see the mass unit here in terms of kilograms, but most often it's grams per milliliter for liquids and solids. And what we see is, if we have the same volume of something, a foam block and an iron block, that's 1 cubic centimeter or 1 milliliter in volume, they have very different masses. And that's because of the density, the packing of the molecules in this volume of space. The packing in foam, those molecules are much farther apart, giving us a lower density. Versus in iron, those iron molecules are packed very closely together, very tightly together, and it gives us a much higher density, a larger mass per volume. So let's look at a calculation that we can do with density. I have 73.2 milliliters of a liquid, and that has a mass of 61.5 grams. So what is the density in terms of grams per mil? This is really straightforward. I'm given values in terms of mass and volume, and those units are grams and milliliters. I don't have to do anything except divide one into the other. So density is grams per mil, so that's how I set up my ratio. Mass in the numerator, volume in the denominator, I get 0.84 grams per milliliter. This is the density for this liquid. Matter with a higher density settles to the bottom, and with a lower density floats on top. That's why oil and water, oil has a lower density than water does. That's why it floats on top. Sand has a higher density than water. That's why it settles to the bottom of the container. And that's what we see here. Oil with a density of about 0.9 floats on top of water. When we get to things like ice, even though ice is made of water molecules, that as that water freezes, that traps air inside it, so that and gives it an overall lower density, and that's why ice does float on top of water. So as we do change temperature, we see that the density of water does slightly change. It does decrease as I go to lower and lower temperatures, but for all intents and purposes, the density of water is 1 gram per cubic centimeter, or 1 gram per milliliter. Cubic centimeters and milliliters are the same conversion. So it's usually safe to assume when we're doing density of water that we just assume that to be 1.0 grams per mil, unless we're told specifically otherwise. Okay. Very good, everybody. I'm going to leave things here. I've been talking for a while. I would recommend getting into the OWL homework at this point and doing some of these calculations, doing some of this work with some of these conversions and such, and getting comfortable with this. If you have any questions at all, please reach out right away. Right? Thank you very much.